Swayam Prabha. Digital India. Educated India.
Welcome. So we are in the second lecture of the module 3, where in the previous lecture we have studied the different weighted residual methods. For instance, the standard Bubnov-Galerkin or the Galerkin, Petrov-Galerkin, and then least square problems. And also we have just discussed what is the collocation method. Now we also discussed that what is the main difference between the Rayleigh-Ritz method and the standard Galerkin or the Petrov-Galerkin or the weighted residuals method. In general, weighted residual method requires a higher order differentiability, and the weight function need not to satisfy the homogeneous boundary condition, but keep in mind that approximating functions, the approximating basis function, need to satisfy the homogeneous boundary condition at the boundary where the field variable is specified. So this is the main distinction between weighted residual or the Galerkin method and the standard weighted integral statement based on the Rayleigh-Ritz formulation. Now in another way we can view it in this way, that weighted residual methods are a kind of error orthogonalizations. On the other hand, the Rayleigh-Ritz methods can be thought of as a energy minimization. In case of a structural mechanics problem that we will be dealing with here, that weighted residual methods and the Galerkin methods are mostly equal. We will be obviously doing the integration by parts, and which will probably lead to the Galerkin and the weighted Galerkin's formulation and the Rayleigh-Ritz formulation are same for the cases we will study. The objective here is to understand what is the different kind of approximating technique exist or the different kind of approximation exist here, where we need to cater the all spectrum or the all kinds of the problem, where we need to we can take care of the all kind of problem where the standard integration by parts cannot be performed, and or there we can apply the standard weighted residual methods. But here in this lecture, what I will describe through an example, that what is the different weighted residual methods we have learned, that I will discuss in this lecture through an example, and we'll find out that what different type of approximation exists. But before that, let me go through a simple Rayleigh-Ritz method. Let us take a problem. So suppose there is a differential equation of this form. So I choose a simple differential equation. This example problem can be found out in the Professor Reddy's book on finite element. So this is the domain of application, and this is my Dirichlet boundary condition, and this is my Neumann boundary condition. You see, the exact solution of this differential equation is looking like this. So this is my exact solution, and the standard n parameter approximation is simply ux cj phi j and phi 0. So phi 0 is due to this boundary condition which is homogeneous here. So naturally, in case of a Rayleigh-Ritz method, the phi 0 can be 0, right? So now if I will look into two parameter approximation, so let us see this two parameter approximation is C1 phi 1 and C2 phi 2. So this is my approximation. So first what we will study is that how to approximate how to solve this problem in a standard Rayleigh-Ritz method. So let us first learn the Rayleigh-Ritz method. So in case of Rayleigh-Ritz method, this approximation looks like this, and this is my standard approximation. So here first thing we do is to construct the weak form. So that is very same that we did it earlier lecture in the earlier module. So what we did our differential equation was this, that is minus of d2u dx2, and then there was a plus u, and then there was plus x square. Sorry, it was minus u probably. So now if you write the weighted integral statement, so this is this into some weight function w, so this is equals to 0, that is weighted integral statement that we follow in the Rayleigh-Ritz method. Now here what we do is the weight function is my approximating function, so naturally I can transfer the derivatives here. So I just do the integration by parts, which will look like this, because the natural boundary condition will also appear here. So this will be my natural boundary condition here. So now this is just a integration by parts here. Now the main issue is how to choose this weight function and the approximating function. Now the first condition that Rayleigh-Ritz required is that the weight function, first let us find out that phi 0. The phi 0 is 0. So basically u0 is 0 given at the boundary. So naturally phi 0 I can take it as 0 here. So here I take phi 0 as 0. On the other hand, the phi 1 and phi 2, what I need to satisfy is that the phi 1 and phi 2 should be 0 at the boundary at x equals to 0. That means that phi 1 at 0 should be 0 and phi 2 0 should be 0. So these two conditions satisfies this simple x and x square. So I just took the simple thing, simple function. So now this can be looked into this is a complete polynomial because it consists of x and x square. So certainly the lower order polynomials are also included, and the another required thing is that differentiability requirement. You see here the differentiability requirement is the only first order. So that del u del x or del w del x should not be 0, right? So that minimum function that satisfy is phi 1 is x. So naturally I took the phi 2 as x2 x to the power 2. Now if I just substitute these approximations, so my final approximation is this. Now in case of a Rayleigh-Ritz I take this. So now w1 and w2 are x and x square. So if I just substitute, I get two such equations, 1 and 2. Now if I solve these two equations, I will get C1 and C2. So which I solve it, and then what I observed is this, that what is the solution. So let us go to the solution. So here I solve the this thing, these two differential equation. So these two linear equation, and then these two equations is, if I find out, then I will get that C1 and C2, this is this, and so this if I substitute this C1 and C2, so this looks like this. Now if I so here there will be no plus. So now if I look this equation and then if I compared with the exact solution that I described previously, so the exact solution is for this problem is this. So the exact solution is this. Now if I solve this problem here, so now if I plot it between 0 to 1 at some discrete point, what I did is I choose 100 points. Okay, so in the plotting software, I just took 100 points and plotted. So if you look carefully, that the exact and the Rayleigh's approximation is almost matching, so visibly there is no difference. But if you now compute the error, so what I did is essentially I obtained two vectors, that is U Rayleigh's and U exact for so these two I choose the norm between them. So then I take the relative norm. So essentially this is the relative norm is the error I write as the error. So which is URR minus, or rather it doesn't matter because it is whether plus or minus, so it doesn't matter because it's a transpose. So URR minus U exact so this is error is U exact minus URR. URR is the Rayleigh's. So this transpose U exact minus URR divided by U exact transpose by U exact. So this quantity I just square root. Okay, so this is the error. So this error I plotted. So that's how I reach a scalar value. Otherwise I cannot compare different method. So I just choose this, and then I found that this quantity is 4.8 into 10 to the power minus 3. So now this gives an idea how my approximation, how good is my approximation. So this is the, sometimes we can say the vector norm or relative vector norm, relative error sometimes. So this is error is relative, so because we divide it by the exact solution. Now this is for the Rayleigh's method. So if you look carefully, that our exact solution was involving trigonometric function. Even with such a simple approximation, we could efficiently or the sometimes the acceptable results with the Rayleigh's method. Now moreover, here in case of a Rayleigh's, if you look carefully, that this weak form is a symmetric bilinear form, because if I just transfer U and So if I write it that W of U is B of U comma W. So this is a symmetric bilinear form. So naturally I can construct its energy. So this is my energy associated with the differential equation. So what Rayleigh-Rinz essentially tells that even with the same approximation, if I substitute here and minimize, if I write this as my phi, then if I write d phi dCj is 0, so or in specific case here d phi d pi by d c1 equals to 0 and d pi by d c2 equals to 0, I will get the same solution because the weak form corresponds to this energy functional. So the first variation that we have learned is essentially 0 is nothing but the bu b of w comma u, or the delta u here I can write it as this. So this we have already discussed, but I just u is L of delta u. So this is the weak form. Now this will lead to the same solution. So we can see it as an energy minimization. From the energy minimization concept, we can see it as an energy minimization. Now in case of a standard Galerkin or the Petrov-Galerkin, let's see how it looks like. So now let us see the standard Petrov-Galerkin method or the Galerkin method. So let us see first Galerkin's approximation. So in the Galerkin's approximation, you see again we need we are restricting ourselves these two. So this approximation, two-term approximation, and obviously the Galerkin's approximation is Wx. I will choose the phi I. So that's my Galerkin's approximation. Now what is the requirement for the Galerkin's approximation? Now phi 0 here, that phi 0, since there is no natural boundary condition is evolving in the weighted residual technique unless we perform the weak form or the integration by parts, unless we perform the integration by parts, then our phi 0 need to satisfy the Neumann boundary condition also. So naturally phi 0 0 should be 0 and phi dash 0, which is coming from here, is has to be 1. So these two conditions I have to satisfy. So the first thing we notice that our phi 0 was 0 for the Rayleigh-Rinz function, but here phi 0 is phi 0 will be different because the phi 0 not only has to satisfy this condition, but phi 0 also satisfy this condition. So the first derivative of the phi with phi 0 with respect to s has to be 1 at x equals to 1. So this condition satisfies through this. So if you look that phi 0 x is now my x. So now in case of a phi 0 that we have used for the Rayleigh-Rinz method was 0. So now the first thing that you notice that the phi 0 changed here. Again, what I need to I think this is something wrong here. So this has to be 0. So now the second thing that what we need here is that my approximating functions phi i's and phi 2's need to satisfy the homogeneous boundary conditions. So what is my homogeneous boundary condition? That is phi I 0 should be 0 and phi dash I at 1 has to be 0. So if I need to satisfy this, I can easily construct this function. So there are two conditions, that is the first two the two conditions. So if I take ax plus b and then find out what is x and what is b, then I can construct this kind of function. Or that is not possible because there is a differentiability requirement here. So naturally something like ax square plus bx plus c kind of thing I have to choose. Then what I achieve, that phi 1 is something like this and phi 2 is something like this. Now this phi 1 and phi 2 satisfies this condition as well as this condition. So this is, if you look carefully, that in case of a Rayleigh-Ridge method, what was our phi 1 and phi 2? So phi 1 was x and phi 2 was my x square. So this one is a linear, then this one is quadratic. Now if you look carefully, that this is my maximum highest order of polynomial present here is the quadratic, and here the highest order is cubic. Now if I look this approximation, so this is a cubic polynomial, right? Now you see why I need to choose this cubic polynomial, because our differential equation was a second order differential equation, not a so our differentiability requirement increased compared to the standard weak form that we dealt with the previous case. So here the residual is second order derivative. So naturally you see that phi the order of the polynomial have increased. Now this is one of the distinctive feature of the weighted residual method. So now if I substitute this quantity here, so I can get this quantity. So this quantity is nothing but the residual. So residual contains two thing. One is two unknowns, that is C1 and C2. So these two are my unknowns. So I choose I have chosen phi 1, I have chosen phi 2, I have chosen phi 0. So the unknown quantities are this. So now I write the weighted residual statement, which is phi 1 r equals to 0 and then phi 2 r equals to 0. Then again I just substitute this, and then this r I will substitute, this r you can compute it, so this r I will substitute, and then I get two linear equations, 1 and then from here 2. So with these two equations, if I solve it, then I get my solution is of this form. So this is you see in our previous case our solution was a quadratic solution. Now this is a cubic solution. So obviously the this Galerkin method requires of higher order differentiability, and there are another important thing here, that these conditions, that phi 1 and phi 0 or phi i's and phi 0 need to satisfy the non-homogeneous Newman condition here also, because the Newman condition doesn't appear in this equation. This equation doesn't if I choose a phi 1 and phi 2 in these two equations, the Newman condition is not satisfied here, which was automatically satisfied in the weak form. So this is one of the distinctive feature of the Galerkin formulation. So now what I will do is that I will show you that the same exercise I did it in the previous case. So what is the corresponding solution? So now So now here the same exercise I choose. Now here if you look carefully, that our Galerkin solutions are little better because it is some less, the norm is less compared to the previous one. So here there are two things here. One thing is that obviously the Rayleigh solution was a quadratic solution, and Galerkin solution is a cubic solution, cubic approximation. So obviously this will give me me better result, but this is always not true. That I will show you in the some exercise. Now here if you look carefully, that Galerkin, Rayleigh and exact are not visibly much different compared to the exact solution. Now here then what we choose is the Petrov-Galerkin approximation. The same way that Petrov-Galerkin, the only weight function is different compared to the previous case. Now the weight function here, instead of phi's, I can choose psi. So the size I choose is phi 1 and phi 2 is x and x square. So you see here that phi 1 and phi 2 is psi 1 and psi 2 is different from phi 1 and phi 2. So this is the main difference with the Galerkin and Petrov-Galerkin method. Now in the Petrov-Galerkin method, the same way that we perform the Galerkin's approximation, that R we can construct, the R I can substitute, and then I use this. So these two equations are my linearly. Obviously this size which I take different size here, which is a requirement for Petrov-Galerkin. Now this size has to be complete. It has to be complete polynomial, and obviously this has to come from the differentiability requirement also. So now that phi should come from the differentiability requirement. Now this has to be the complete polynomial to obtain a linearly independent system. So now this if I just perform the same exercise that we did earlier for the Galerkin case, we obtain this kind of solution for the Petrov-Galerkin method. Now I will show you that, but the important thing is that the phi approximation or the field variable approximation remains same. So there is no change the field variable approximation compared to the Galerkin method. Only change is that the weight function, instead of phi i's, I choose weight function as psi i's, which is different from phi i's. So which is x and x square here. That's the main difference. The rest of the procedure is same. Now how to choose psi i's? Psi i's has to be psi I has to be chosen in such a way that it should give to a positive definite system, so that I can invert it. So now the next thing I will show you that how to what is the approximation leads to. So this approximation again I plotted in the same way that the previous cases. So let me show you how. So the same thing that I did for the Rayleigh, I did for the Galerkin, and I did for the Petrov-Galerkin. If you look for the Petrov-Galerkin, I get little higher here, but it is very comparable with the Galerkin. Now again the coefficients are different. If you look carefully, that solution for the Galerkin C1 C2 and solution for the Petrov-Galerkin, which is C1 C2, both two coefficients are different. So the same thing, the solution is distinctively not very different, but if you compute the error norms, then you will see that Petrov-Galerkin gives 2.4 into 10 to the power minus 3. So this is done with the 100 points. Now the next thing I will solve with the least square method. So in the least square method, again the approximations remain same. So approximation doesn't change at all. So the approximating functions, I take these two functions. So only change is that psi I is del r del Cj. So here how what is the meaning of this? It is the meaning of this is that I integral of r square, I just wanted to make 0 or minimum, so that is the requirement. So I just take the normal equation del r by del del x or del Cj. Essentially Cj's are my unknowns, so r will contain Cj and phi. So integral of r square d omega, this is my normal equation. So I can just take the derivative inside the integral. So here, so this is always not the case. So del r by del Cj r d omega equals to 0. So this is my normal equation. So now if I look it carefully, this is nothing but my psi, sorry, this will be G, not J, this will be I. So this is del Ci, so Ci, so psi I r d omega must be equals to 0. So this is my least square solution. The same way, the only change is the weight function. As I described in the previous class, that the least square method or the Galerkin method or the Petrov-Galerkin method or even the collocation methods are essentially different weight functions. Because of, so based on the choice of the weight function, we describe this different method. So now if I just choose this my weight function psi i's are del r by del C1 and del r by del C2, again with the similar kind of exercise, this is just you can compute it by hand, you can substitute these two and then you will get again two linearly independent equation. So now these two equations if I solve, then what I will get is that these solutions. Now if I now plot these two solutions, then I will see that how my error is looking like. So let me show you how the error looks like. So my error looks like this. So you see that in case of a least square solution, the coefficients are different again compared to the Galerkin and Petrov-Galerkin. So the on the other hand, Rayleigh-Ritz is this. So this will not be plus. So Rayleigh-Ritz will be this. So now if you look carefully, that the errors, that error I computed, I explained previously, that error is very much close to Rayleigh-Ritz method. So least square solution doesn't give the very good answer here. So it is always not so even though the least square function is essentially a cubic polynomial, so it is not necessary that the if you choose higher order functions or higher order approximations, you will always get a better solution. So this is one of such example. Now here if you look carefully, that then we'll see that these errors, even though the solution is not visibly much different, but least square solution is even though having a quadratic polynomial, cubic polynomial, solution is a cubic polynomial, this has a higher order polynomial compared to the Rayleigh-Rinz method. So error is very similar to the Rayleigh-Rinz method. Now Rayleigh-Rinz method, if I use my cubic polynomial, so Rayleigh-Rinz method, obviously it is not good, or it is not justified that we can compare the Rayleigh-Rinz with the Galerkin here. We have to choose actually for C1 phi 1, C2 phi 2 and C3 phi 3. So Rayleigh-Rinz for this problem phi 0 is 0. So if I choose like this, then obviously Rayleigh-Rinz method will give a better solution, and obviously this will have a cubic polynomial. So this is one of the important things. So C1x plus C2x plus C3x is cubed. This kind of approximation if I choose, and if I choose a fourth order polynomial, then it will match with the exact solution. So that you can try and see how it looks like. So this is the example I wanted you to show, that what is the different methods first of all, and what is the basic difference between these methods, including Rayleigh-Rinz method. So weighted residual methods, again I reiterate that it is the weight function that we the restriction that we pose in the weight function in the Rayleigh-Rinz method, we remove that restriction in the weight function in the weighted residual method. So in a sense, weighted residual method is the generalization of the Rayleigh-Rinz method first, and second, the consequence to this is that weight function can be taken or can be chosen independently of the approximating function, but approximation function in case of a weighted residual method need to satisfy all requirement of the Rayleigh-Rinz method. This is one distinctive thing you have to note. And second thing is that it is not necessary that we perform the integration by parts in the integration by parts for the weighted residual method. It is not necessary, or you may perform, we may not perform, but if we perform, then our natural boundary condition will be there due to the integration of by parts, even in the Galerkin's method or the weighted residual method. But in case of a general weighted residual method, natural boundary conditions need not to be imposed, or it need not be means it will not automatically arise in the formulation. So you have to impose the natural boundary condition. So that poses us another difficulty in the if we don't perform the weak form, and choosing such functions is difficult mainly. And then obviously if we don't perform the integration by parts, our differentiability requirement increases. So in general, the weight function the weighted residual method requires a higher order polynomial approximation or higher order approximation compared to the standard Rayleigh-Rinz method. So, and one of the method can be, the weighted residual method can be viewed as an orthogonalization compared to the Rayleigh-Rinz method, which is a minimization. So this is the main difference. So now you see, we all learned here the global approximation. So one of the main difficulty of this kind of global approximation is how to choose these functions, that is phi's and psi's. So this is very easy for simple differential equation and simple problem with a simple boundary conditions, but our objective is to construct a method or construct a procedure by which we can apply this procedure or the method to a global or any kind of problem, or a more practically applicable problem This is, for instance, if the boundary condition is complicated, if the geometry is complicated, then choosing such function is very difficult. It is not possible at all. So we have to bring it down to such level that in such cases we can also approximate it, and this is a foundation for those approximations or the approximating procedure. Now this is where the global approximation, we choose a local approximation where the finite quantity, the finite element, the finite name comes from the finite quantity. So finite number of approximations comes from the local approximation. So that we will start in the next class. So here I stop in this thing. So let us meet for the next class, where I will start the axial problems. Thank you.